In a lab in Boulder, Colorado, there is a robotic arm with no motors inside it, no gears, nothing spins. When it lifts something, the only parts that move are thin plastic pouches filled with liquid, and they contract silently, the way a muscle does. For more than a century, almost every machine we built to move something has relied on the same idea: magnets, copper wire, and rotation. Your car, your factory, the robot arm that welded your car, the hand of every humanoid robot being built right now. All of it spins first, then converts that spin into useful motion. American engineers are now trying to delete that step entirely. And for 40 years, everyone who tried this failed for exactly the same reason. Before continuing, take a second to subscribe so you don't miss anything, and let us know in the comments where you're watching from. To understand what's being challenged, you have to understand what it's replacing, and how good it already is. The electric motor is one of the most successful inventions in human history. Spin a magnetic field, and a rotor follows it. That single trick powers roughly half the electricity consumed on Earth. But a raw motor is almost useless for a robot. It spins fast and pushes weakly. A robot joint needs the opposite: slow, precise, and strong. So in 1957, an American engineer named C. Walton Musser patented something called strain wave gearing, the harmonic drive. A flexible steel cup deformed by an elliptical hub that could trade enormous speed for enormous torque inside a package the size of a hockey puck with almost no play in the joint. That combination, electric motor plus precision gearbox, became the standard body part of every industrial robot on the planet. Millions of them. Every welding arm, every surgical robot, every humanoid prototype you've seen on the internet. To replace that, you'd have to beat something that already works extremely well. Here's what happens inside a single robot joint. Electricity enters a coil of copper wire and creates a rotating magnetic field. A rotor chases that field and spins, often thousands of revolutions per minute, with barely any strength behind it. That spin enters the gearbox. Inside, a flexible steel ring meshes with a rigid one that has slightly more teeth. Each rotation advances the flexible ring by only a tooth or two. Speed collapses. Force multiplies, often by a factor of 100. Then an encoder counts the position thousands of times per second, and a controller decides how much current to send next. Motion, reduction, measurement, correction. Repeat. Multiply that by 6 or 7 joints per arm, and by 2 arms, 2 legs, and a hand with 20 fingers worth of movement, and you start to see the scale. A modern humanoid can contain more than 40 of these assemblies, each one a small precision machine full of steel. But there's a reason engineers keep looking for something else. The problem isn't the physics, it's everything wrapped around it. Gears wear out. That's the whole story, and it's bigger than it sounds. Every one of those meshing steel teeth is a surface grinding against another surface. It needs lubrication. It generates heat. It accumulates microscopic damage. Precision gearboxes are frequently the single most expensive component in a robot arm, and in a humanoid full of them, actuation can dominate the entire bill of materials. Then there's the second problem: rigidity. A geared joint is stiff by design. That's exactly what you want when you're welding a car door in a cage. It's exactly what you don't want when the robot is holding a strawberry, a surgical instrument, or a human being. A rigid joint that meets an unexpected obstacle doesn't yield. It either breaks something or breaks itself. Engineers spend fortunes on force sensors and software just to fake the softness that biology gets for free. And there's the noise. Rooms full of industrial robots whine. That single detail quietly disqualifies the technology from hospitals, homes, submarines, and anywhere else a machine is supposed to blend in. So, is there a better way to make something move? The alternative doesn't come from magnets at all, it comes from static electricity. You've felt it. A dry winter day, a wool sweater, a doorknob. Opposite charges attract across a gap. In 1880, the German physicist Wilhelm Röntgen, the man who would later discover X-rays, sprayed electric charge onto a strip of rubber and watched it stretch. Nobody did much with it for over a century. Then, in the 1990s, researchers at SRY International in Menlo Park, California, returned to the idea. Their version was elegant. Take a thin sheet of soft rubber, paint flexible electrodes on both sides, and apply thousands of volts. The electrodes attract each other, squeeze the rubber flat, and the material spreads outward. By 2000, they had films stretching to more than double their original size. They called it artificial muscle. And unlike a motor, it doesn't spin and then convert. It simply contracts directly, the way tissue does. No gears, no lubricant, no rotation, almost no current, because electrostatic force is about voltage, not amperage. Silent by nature, soft by nature. It should have replaced the motor 20 years ago. There was just one problem, and it destroyed nearly every prototype ever built. Push enough voltage across a thin insulating film, and eventually it fails. The electricity punches straight through and burns a hole. Engineers call it dielectric breakdown. For solid rubber artificial muscles, that was fatal. One microscopic pinhole, a speck of dust, a manufacturing flaw, a moment of overload, and the actuator was permanently dead. Not weakened, dead. There is no repairing a hole in a solid sheet. And to get useful movement, those films had to be pre-stretched and held under tension by rigid frames, which meant the soft actuator was bolted into a hard, bulky skeleton that ate most of its advantages. So for roughly 2 decades, artificial muscles lived in the same place. Spectacular demonstration videos, conference papers, and drawers full of failed samples. Astonishing performance right up until the moment it wasn't. The physics was never in doubt, the engineering was. Then, a graduate student in Colorado asked a question that sounds almost too simple. What if the insulator didn't have to be solid? At the University of Colorado Boulder, Professor Christoph Keplinger's lab was working on exactly this dead end. Erica Combe had joined the group as a PhD student after seeing a video of a rubber actuator moving so fast it outran the camera's frame rate. The change they made was almost embarrassingly small. Instead of a solid rubber film, they used a flexible plastic pouch filled with an insulating liquid. Apply voltage, and the electrodes on the outside begin to zip together from the edges inward. That zipping squeezes the liquid, forcing it to the far end of the pouch, and the pouch contracts, pulling its ends together like a bicep. The consequence is the important part. When breakdown happens now, the fluid simply flows back into the gap. The insulation reforms. The actuator keeps working. They called them HASEL actuators, hydraulically amplified self-healing electrostatic. The results were published in Science in January 2018. The performance figures, over 300 watts per kilogram of power to weight, response times under 10 milliseconds, no metal, no heat, and effectively silent operation. Linear motion produced directly with no gears or cams to convert it. Muscle-like, not metaphorically, measurably. A company called Artemis Robotics spun out of the Boulder lab in 1919. The name is a compression of artificial muscles. In February 2026, they announced a new generation of contracting actuators with more than double the mechanical output of the previous version, fully encapsulated, and began seeking partners for robotic hands, from humanoids to industrial automation. But the hand may not be the biggest prize. Because the actuators are silent and low profile, they're being explored for haptics that reproduce texture and pressure. The U.S. Department of Energy funded work using them in soft underwater vehicles, arguing the approach could cut the cost of an unmanned submersible by up to 50 times. Non-magnetic, pressure-tolerant, prosthetics, exoskeletons. Now, the honest part. These actuators need thousands of volts, which means dedicated high-voltage electronics on every machine. The company remains small, around 7 employees, roughly $4.5 million raised, mostly from grants, with no publicly disclosed commercial deployments or independently published benchmarks. Working in a lab is not the same as replacing a 100-year-old industry. Picture a robot that moves through your house in complete silence and yields when you push it. If artificial muscles beat the electric motor, should robots be built to feel human or stay obviously machines?